Today, we're going to talk a little bit about the periodic table. The periodic table has been around for a long, long time. Not nearly as long as mortuary science, but it's been around the block a couple of times. So, with the periodic table, it began to be developed by a man named Dmitry Mendeleev, a Russian in the 1850s and 60s. Working with Lothar Meyer, a German, they found that these certain elements had similar properties. As elements got larger in atomic mass, some of those properties began to be repeated. Years later, we started being able to put some of these other things together. For instance, hydrogen has an atomic number of 1. It's a colorless gas that's very reactive. So we're looking at this particular table right here, and I'll expand it out for you. What we find is we have a lot of physical properties that are listed here in the middle. So hydrogen is a colorless gas. That is a physical property. However, it being reactive is a chemical property. So we have a listing of chemical and physical properties here. And we see how reactive it is in terms of can it react with chlorine or sodium or with oxygen or magnesium. And in this case, hydrogen will react with both chlorine and oxygen, so it's quite reactive. But helium, on the other hand, having an atomic number of 2, doesn't react with either. And so we can start to track all of these kind of things. So for instance, if we look at the hydrogen, we see hydrogen is reactive. When we go down a little bit, we see that lithium is very reactive. When we go down a little bit more, lithium is a metal, so we go down and we look for the next very reactive metal. What we find is we get sodium. And when we track that down farther to look for the next metal that's very reactive, we see we have potassium. And so you can start to trend these things. So for instance, between lithium and sodium, we have a certain number of elements. If you look between sodium and potassium, we have the same number of elements. And so we start to see that this distance that's right here and this distance that's right here, because this distance is the same as this distance, we start to see a thing that we call periodicity. And this is something that Meyer and Mendeleev discovered. You can see something similar as we go to the next element. So if we look at the next element, the next one is a beautiful element of beryllium. Beryllium is less reactive than lithium. If we look at magnesium, the next one down, it's less reactive than sodium. If you look at potassium, calcium is less reactive than potassium. Notice that you have the same periodicity, the same number of atoms in between. So what we start to see is a pattern develop. And this pattern, when we have put it together years later after Mendeleev, we get to see that lots of these elements can fit together in these patterns to be groups. And the way we group these things are like sodium, potassium, rubidium, fluorine, chlorine, bromine, iodine. We start to see that these things can be arranged. And what Mendeleev did that was so revolutionary is he put them into vertical columns and called them groups. Sometimes we call them families. Remember, families tend to have the same idiosyncrasies from generation to generation. This is something that is very well known in psychology. So they kind of took this observation of humans and put this onto chemicals and elements. So Mendeleev's periodic table kind of looked like this. Now, what I want you to notice is there were some gaps in this periodic table. So there's a gap right here. There's a gap right here. These elements weren't discovered, but what Mendeleev did is he said, we might not have these things right now, but I bet you there's something that's going to belong there in the future. So when you start looking at some of these things and you start to see, well, something's got to belong there in the future, what we find is we found them. It just took a little bit of time. And so we ended up with this as kind of our massive modern periodic table of the elements, or periodic chart. Now, we label this in all sorts of different ways, and what I want to draw you to is this way right here. There's a number that's on the top of the periodic chart's columns. So those tell you the group number. So this first bit right here, this first group right here, this first column is group number 1. Then we have a second column that's group number 2. And just like you can have groups, these groups, this group number 1, all kind of behaves the same way. So hydrogen, lithium, sodium, potassium, all are very reactive, and they actually get more reactive as you move down. Beryllium, magnesium, calcium, as I mentioned earlier, are all similar in their reactivity as you move down. So we have these little groups in columns, and so I'm waving my hand to show you the column that you cannot see. These groups have similar reactivity, chemical reactivity. So what we do is we base the group assignments. Those group assignments are based on, largely, it tends to be chemical properties. Now, as a result, many of the physical properties are similar as well. So most of the metals in group 1 are very soft metals. Now, we have not just columns, so these group/column assignments, we have those, but we also have something else. We have something called periods. Now, periods are a different beast. They go from left to right. These periods just go 1, 2. Then we start with, that's period 1. Then we end up with period 2. So what all this does, these periods arrange elements not by chemical properties, but by atomic number. Now remember from our lecture on atomic structure, atomic number is in fact our number of protons. So hydrogen has 1 proton. Lithium has 3 protons. Beryllium has 4 protons. And so we just numerically order the number of the periods in terms of your atomic number. And what we find is when we start looking at this larger periodic table of the elements is that much of this is very, very predictable. I call this thing, and this is kind of just me talking, this is what I'm going to call the best cheat sheet ever. Because when you can learn what the periodic table of the elements is all about, what you do is you learn how chemistry works. It's pretty amazing. Mendeleev, when he was doing this, only had masses to work with. He didn't know about the atomic numbers. And so you have chromium here that has an atomic or a mass of 52. Manganese, he would know, had a mass of 55. Iron would have a mass of 56. And so he arranged his periodic table based on masses. So Mendeleev worked by mass, but now then we work by atomic number, or number of protons. What's interesting here is the number of protons begins to feed into what we know about the reactivity, because the electrons do the reacting. So how does this play out on different kind of things? So the periodic table, we've already talked about groups, we've already talked about periods and what those mean. So why in the world would the properties repeat? Niels Bohr was the one who first came up with a somewhat successful explanation. Niels Bohr, this Danish scientist, said that yes, the number of protons determines the identity of the element, right? But the number of electrons talk through the chemical's reactivity, how that chemical reacts. Now, at the time, Bohr didn't really understand how in the world these electrons do the reacting. But he noticed that, if protons don't change, and we can see that the atoms have different charges based on a lot of observations that we can make in the lab, then that means the only thing that happens is that the electrons have to move. And so he was able to observe that and then say, must be the electrons that do something there. And that's kind of right. Elemental reactivity is an interesting thing. Now, if we go look at chlorine, we can find that chlorine is so reactive that it will react with itself rather than stay as just Cl. It's part of that diatomic 7 that I was talking about. But one of the interesting things is, in our body, we have a lot of this chloride ion. So if chlorine is so reactive that it's going to react with anything it can get its hands on, why is it that when you add a negative charge, you add an extra electron to a chlorine to make it a chloride, it's very unreactive? This is something that bumfuzzled lots and lots of scientists. How in the world can this be the case? Well, I'm quite frankly happy that chloride doesn't react very well, because otherwise life wouldn't exist, because we got the chloride as a balancing ion in so much of life. Well, the answer for why the reactivity begins with the electromagnetic spectrum. In the electromagnetic spectrum, we see that light functions as a wave. So when we're looking at this is just light. That's all the electromagnetic spectrum is about. This is light. Light exists as a wave. So you have a wave that you can see. But what Einstein came up with is that light is also something called a particle. And through a lot of scientists' work, we found that this wave-particle duality of light is really fascinating. So now then, we had this guy named Einstein come up with this thing that says E equals mc squared. We had a guy named Max Planck, another contemporary of Einstein, say E is equal to some constant times this frequency of light. So now then, what we start to see is this frequency actually becomes wavelength, hc over lambda, lambda being wavelength there. So let's go ahead and label some of these things where we're talking about this wave-particle duality. So this here is your mass. This is energy. And then this C right here is the speed of light, typically in a vacuum. But it's the same C that you see right there. Okay? Then you have Planck's constant. Planck's constant is this h here. That's a really, really small number. You have frequency here. That's how many waves pass a certain point in a given amount of time. And then you have wavelength here. So when you start to put all of this stuff together, it looks like it's a discombobulated mess, right? Well, what we end up finding is when we set this energy equal to this energy, now then we have an interesting thing. We have a new formula that we can say mc squared is equal to hc over lambda. So now then we see that we've got wavelengths, that wave of light, and a particle that are related in the same equation. So now then what we find is an interesting thing. We can have this mass of a very fast moving electron that has a certain wavelength of that particular electron. And now then we can measure how much energy that electron could have. So all of this is now related to the electromagnetic spectrum. And what we find is the farther you go from left to right, the shorter the wavelength is. So we have short wavelengths over here and long wavelengths over here. So this gamma ray, see Bruce Banner for example, is actually a high frequency. High frequency means it's very destructive. It will destroy atomic nuclei if we're not careful. But when you have a low frequency, kind of like radio waves that are the size of buildings or humans, now then what we've got is something that is not near as destructive biologically, but it also doesn't react with all sorts of things. So when you start looking in this range right here, you start to see light interacts with matter in a very, very peculiar way that is designed, that is patterned after how these electrons way over here, how these things, these electrons, do chemistry. It's about not just their mass, it's about their energy. It's not about number of electrons, it's about the energy of the electrons, which we measure using the electromagnetic spectrum. So that's a quick, brief overview on how that plays out. This Bohr model of the atom was kind of interesting. He used atomic emission spectroscopy, where he was able to shine light on atoms. They would give off something kind of like a neon light, a little bit of an emission or like fireworks. And what he did was he said, okay, well you have, let's go back to this. We have a nucleus here, whatever that nucleus is. Well, if I put one electron over here, and I have that electron orbiting that nucleus, it has a certain energy. This energy is a really high energy electron, okay? Because it's close to that nucleus, and it has to be a high energy so it circles the nucleus and doesn't fall into the nucleus, because that would be awkward, wouldn't it? Well, what if we put another orbit around and we put another electron here? This energy of this electron, it doesn't have to move quite as fast to be able to avoid going into the nucleus. So now then this one would be a low energy electron. And when we start to put all this stuff together in 3D, so this is a two-dimensional model, when you put it together in a 3D model, what we find is we've got this one right here, and then we'll have one electron that's kind of orbiting like this, and we might have another electron that orbits here like this, and we might have another electron that orbits like this, and we might have another electron that orbits like this, and then we might have hold on, let me do a different color. Let's have another electron that orbits a farther piece out, and one that orbits way out here, and one that orbits way out here. And so what he basically said is, that electron that we started with, that one that's right here in the middle, that one right here, that one's so far in the middle that you can't get to it. So if we have something called light, and that light goes and hits that electron, now then that electron can go flying off. When that electron goes flying off, it emits a certain amount of energy. And so as it flies off, it's going to emit a different kind of energy, a different wavelength of energy. It's pretty amazing. When you look at how this plays out, the pink electrons emit an energy that is lower energy. So this is kind of a low energy kind of thing. Remember, they're not moving as fast. It takes a lot of high energy for that. So like the light, it has to be blah, 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 blah. It has to get through all of those really fast moving electrons to hit that green electron. And when that green electron gets hit, it gets sent out super fast, and it emits energy too, but this energy that it emits is really high energy. And so now then, what Bohr basically came back and said was, because of the location of those electrons and how fast they have to spin around that nucleus to keep from falling in, just like with the astronomy, now then what we find is those inner electrons have higher energy. And so now then we have different emissions for different atoms. And so we can start to figure out which electrons are more reactive. So the Bohr model looks something like what I've already talked about. So you've got a lowest energy and you got a higher energy. So what happens if I take this electron right here and I kick it up to this state right there? So I go from a ground state 1 right here to this is a number 1 to a number 2 here. And so if everything is set at different radiuses and are fixed, then we can start to see some of these variations. And if this 1 can go over here to a 3, then we're seeing something different. Or can we go 1 to 4? Or could we go 2 to 3? We have all sorts of different opportunities here. And this is kind of getting closer to right. So he called this ground state a ground state level of 1. Because if you really look at strict definitions, 0 is a placeholder, it's not really a number. -0 would be ridiculous. So, with the Bohr model, he said that this is how you can explain some of the energies. Well, not quite. While we can jump from 1 to 2, or from 1 to 3, and get different energies from your atomic emission spectroscopy, like Bohr was talking about, it's actually a little bit different than that. It's closer, But as you well know, so much of life is about not stating how something truly is, but getting close to what it seems to be. So that's what we're dealing with here. So a guy came back sometime later named Ernst Schrödinger, or for those of you who aren't Germanic in origin, Schrödinger, came up with a thing that involved an equation called well. No, the equation wasn't called well. Came up with an equation called Schrödinger's equation. Now, Schrödinger's equation basically comes back and says, well, to categorize, it allows you to catalog your electrons by, in part, energy, by magnetism, or by energy, symmetry, by energy, by symmetry, by magnetism, and by spin. And so if we can catalog electrons by these 4 different things, these things gave us 4 quantum numbers. And out of these 4 quantum numbers, the one I really want to focus on is this energy. So this energy quantum numbers, that would be 1, 2, 3, so all that kind of stuff, okay? So that's called your principal quantum number, okay? Now, these quantum numbers are these energy levels, if you will. It's kind of like being on a ladder. So when we're looking at how that plays out in terms of your quantum numbers, what we have is we have hydrogen that only has 1 electron. If hydrogen only has 1 electron and its ground state is 1, in the absence of applied energy, then we just have 1 electron in the number 1 ground state. So what we can also do is we can start to see that there's some similarities as we move across a period. You see that hydrogen and helium are the only things in that first period, or that first row. As a result, these things right here are n equals 1. So there's our n equal 1. So now then, if we start to look at this, if this is n equals 1, then isn't this period the same as your n? So what this allows us to do is to kind of quantify the relative energies. So now then, we have an n equals 2. The energy is higher, so we have a higher number. Remember, lithium is a very reactive metal. It said hydrogen up above when we were looking at the properties was reactive, but lithium is very reactive. And what we know from experience is we can put lithium in some water and it'll react, but if we put sodium in water, it really reacts. So sodium, where you have a n equals 3, it has electrons in a 3rd energy level on rung number 3 of the ladder. If you throw potassium in water, you can look all this stuff up on YouTube. You look up potassium in being chucked into some water, it explodes. So now then this n equals 4 basically says we got a whole lot of energy stored up in that 1 potassium. There's a thing that I saw on YouTube the other day where they dumped rubidium into a bathtub of water. It exploded, this bathtub. It has an n equal 5. Could you imagine what cesium CS would do with an n equals 6? And Goodness help us if we end up getting to this francium that has an N equals 7. Do you realize how reactive francium has to be? If rubidium blows up a bathtub, what's cesium going to do? What's the same amount of francium going to do? It's impressive. And so what we can start to do is we can use the atomic emission spectroscopy to dictate where the electrons are and how much energy they actually have. Fascinating stuff. So now then, we kind of walk through a little bit of this N equals 2 in terms of its energy. But where we're looking at N equals 2 here, we don't. If you look at this going across the periodic chart, we'll use this one because no one uses that very often because it's not so pretty. How many elements do I have there? If you count them, we have 8, don't we? If you look at N equals 3, how many elements do we have? If you look at this thing, it looks like we've got 8. Now you've got something that's kind of weird in the middle. This weird that we have in the middle is pretty fascinating. I'm going to call them, and I can't see that very well. So we're going to undo this. This stuff that we have in the middle here, all this noise, those are called transition metals. Those transition metals kind of work your way from something that's really reactive like potassium to something that's not so reactive like gallium to something that's really reactive like bromine. Okay? Something that's not reactive at all called krypton. And so we have a transition there that's occurring. But how does that work? Why does it work that way? Well, it's kind of interesting. When you look at these things, we have the increasing numbers, and this kind of simplifies a lot of stuff. So we get lots of ways that we can start to classify this periodic table of elements. So let me do this in something that you can read a little bit easier. This stuff in the middle, right here that we were just talking about, this batch right here, this is called transition metals. All of these things are metals. Okay? When we start to look at, we'll go back to this thing, all this stuff right here, all that stuff, these are what I call non-metals, and what most people call non-metals. Now we got some weirdness that goes on in between, and that weirdness that goes on in between comes through, and it's kind of interesting. It goes through these. Nope. It follows right through. So we have boron. So it's this one. It's this one. And this one. And this one. And this one. And this one. Those things, and really and truly, we got a little bit of behavior like that where we find these little corners down here. Those little bits right there. And then you can argue some others actually as well. Those things, I'm going to call them, I'm going to do the pink here. I'm going to call those metalloids or semi-metals. So those things kind of act like metals, but they don't. So we have these transition metals that kind of go through, and we get to something that's more metalloids, and then we end up with non-metals. Notice you got the little stair step right there. Now, we also have down here at the very bottom, this very bottom here, All that right there is something that we call inner transition metals. These inner transition metals, these two things go right up here. It's just easier to write it on a periodic chart if you just put them at the bottom, if you put it on a piece of paper like that. Now there's some other interesting bits of bobbles about this periodic chart, and I'll go to something that's a little bit more interesting. So this group 18 right here, we call them noble gases. All of these things are gases. They're not very reactive. Nobles aren't terribly reactive. They just kind of sit there and do nothing. That was the idea back in the Middle Ages anyway. No one understood what nobles did. They just sat in their castle and ate bonbons or something. So these noble gases are what you aspire to, but they don't actually do anything. So like for instance, this fluorine that's right here as number 17 is always trying to become like argon. To be like argon, who's right next door, we have to add one electron. When we add one electron to fluorine, then it becomes like argon. But fluorine, if we take fluorine plus an electron, don't we get fluoride? Because now then fluorine becomes negatively charged with an extra electron. So it's not really argon, it's just a negative fluorine or a fluoride. Well, if I look at oxygen, oxygen plus 2 electrons then becomes O2 minus. But now then it has the same number of electrons as argon. You see what's happening here? What do you think nitrogen's going to do? Nitrogen might gain 3 electrons to become something that looks like argon. Now, when you go to the other side of the periodic table, we have down here, this is sodium, and this is magnesium, I believe. So with sodium is right here at number 3 right there. But if we take sodium and we do Na, and it loses an electron, so we get an electron that gets popped off, now then we have an Na plus. Well, now then, because of the nature of the periodic table, we begin to send this direction, and lo and behold, because of the nature of the periodic table, whenever you have to go backwards, you end up coming all the way back to the element before. So now then, whenever that sodium loses 1 electron, it becomes like argon. So what you start to see is the metals that are on the left-hand side lose an electron to become like the noble gases. The nonmetals, which are over here on the right side of the periodic table, will gain electrons to look like the noble gases. So we start to see something that's very peculiar. We get all these beautiful things called metals, all these things that are metals, even these things down here are metals, right? These are metals. Will react with the nonmetals. Metals give up electrons, nonmetals grab those electrons, and now then we look like noble gases. This is why sodium gives up its 1 electron, as we talked about in the previous lecture, to chlorine, so that we get sodium chloride, or also known as table salt. This is pretty fascinating stuff. So now then we can start to predict, using the periodic table, how things will react. So what happens if I have this francium that's way down here? How's it going to react with fluorine up here? Well, francium will end up doing what? It's got to go around and end up looking like the noble gas, right? Which noble gas? This one right here. Which one is that? That's xenon. So if it has to go back, or not xenon, that's I don't don't remember which noble gas that is, but it's going to look like that noble gas. So, as a result, now then, francium, it's going to lose an electron and become Fr plus that electron, right? Francium now looks like the noble gas that's circled over here, whichever noble gas that is, and all of a sudden, we can begin predicting things. We don't have enough francium to figure out what in the world to experiment on it ourselves. But we can use our brains and a pattern that we have on the periodic chart to figure out how it would work. Fascinating things, isn't it? All right, so now then, we can start to arrange lots and lots of things in our elements based on their electrons, and that's all I'm trying to get at in the middle here. I don't care how things add or and whatnot. This is not the purpose of this particular course. The purpose of this particular course in this section on periodic table is to show that we can predict reactivity. Neon is extraordinarily unreactive. So, neon is in that periodic table in the noble gases. We have this thing, and I want to point this out here. We have something that I would like to point out called an octet rule. Sometimes I call it a rule of 8, just because. Everything wants to have 8. 8 is the most round number that you possibly can have. Think about it, right? Everything's looking for 8 electrons. How do you get 8 electrons? Well, you've got to gain, you've got to lose. These 8 electrons, when we start looking at things in the periodic table, I'll show you this real quick. Coming over here to the periodic table, when you look at this row right here and this row right here, don't we have a row of 8 across and a row of 8 across right there? As a result, we start to see that there's an 8 that happens. Now, when we need this 8, we need this 8 and we need it quick. So neon already has its 8. That's what I said. It follows this octet rule. Chlorine doesn't yet have its 8. To get 8 electrons, and its outer shell is what we call it, in its valence shell, it needs to do something different. So how is it going to react? That's what we're wanting to see. How can we do this? Okay, so neon is number 10. I think I may have misspoke about argon earlier. So neon's number 10. Let's move on to argon, because this will work better for our particular arguments. So I have argon here. Boop, 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 boop. Okay, so now we got a green argon. Argon's the third most prevalent component in dry air. Argon has 10 electrons. Argon has 10 electrons in the middle. Remember when I was talking about that with the Bohr atom? You can't get to those electrons very easily. But it has 8 electrons on the outside. These 8 outside electrons right here, we call those valence electrons. These valence electrons, you're always trying to get to a noble gas. Argon's already a noble gas, so that's fine. So you need to get to these noble gas configuration. You need to get to the number 8. What if I've got this thing that I'm going to call, I don't know, chlorine right here. In order for chlorine to get to 8 outer electrons, what's it got to do? So chlorine is interesting. So chlorine It also has 10 electrons in the middle, right? But it's got 7 electrons on the outside. 7 valence electrons. So what's it got to do? It's got to get plus 1 electron. When it gets that plus 1 electron, then how many electrons does it have in its valence shell? 8. Do you see what's happening here? We're starting to be able to see a pattern develop. What's sulfur going to do? What's this sulfur right here going to do? It's going to grab 2 electrons to look like argon. If argon's number 18, and we have potassium way over here on this other side, on the left, at 19, what's potassium got to do to get a total of 18 electrons? It's got to lose 1. So we can start to predict a lot of these things. Now, we can do the same thing for potassium. We can do the same thing for bromine. You're going to have a lot of opportunities to figure this out. So we can also figure out kind of how this works in a pictorial way. So for instance, let's deal with sodium chloride, okay? So if I have a sodium, a guy named Lewis came up with a way of saying, you know, if you take a dot, or I'm going to put an X right here, you'll see why in a second, and you put it next to the atom, lo and behold, you get an electron next to the atom. That's all he said. And what we're trying to get to is this thing where you've got lots of electrons around. Notice that there are 8 dots. You're trying to get to 8 dots. Well, what happens if I've got a chlorine also around? Well, yeah, that's a good chlorine. If I have a chlorine that's here, I can set up chlorine like this, can't I? So chlorine is in this group 17 or group 7. So it's going to have 7 valence electrons. This one has 8 valence electrons. Group 16. So this is 17, and I'm going to call it /7. Group 16, and if you look at it, there's 6 right there. It's going to have 6 electrons. What happens if I take sodium, and I take chlorine, and I put them close to one another? Well, you get a pretty amazing thing to happen. You get that sodium to donate its 1 electron over here. And you have the chlorine that still has its 7 electrons. So if you look at this, chlorine now has 8 electrons, but it's got 1 extra electron. So now then that chlorine has a negative charge. Sodium has lost its 1 electron, so it's got a positive charge. But now this sodium that's over here looks like neon because it lost its charge, lost its electron. The chlorine that's right here looks like argon because it's gained an electron. And so you can start to do some of these things. And in fact, one thing that you can do is you can start to design how this plays out with various other compounds. So what if I have a hydrogen that has 1 electron, and oxygen that's got 1, 2, 3, 4, 5, 6, because it's in group 6 or group 16, and I have another hydrogen with 1 electron. What I can do is I can put them all together. And in this case, we don't, because hydrogen and oxygen share their electrons. We'll talk a little bit more about this. This thing now becomes something that looks like this. A hydrogen has a bond, a single bond, to this oxygen, just like this other hydrogen has a single bond to the oxygen. And so now then this oxygen has 2, 3, 4, 5, 6, 7, 8 electrons around it. It has its octet and is perfectly happy. Transition metals are goobers. Technical terms right there. I've already kind of talked through some of these other classifications here. So you got metals, which is the vast majority of the periodic chart. You have non-metals, which are the stuff on the right side of the little dashed line. You got metalloids that are along the dashed line. You have lanthanides. So let me categorize these things by color. So these lanthanides right here in orange are going to be right here. You have actinides, and I'm going to put those in red, are right here. You have alkali metals, and I'm going to change that to a beautiful little yeller just because I can. These alkali metals are these right here. You have alkaline earth, so we'll go with this one right here. Alkaline earth metals are right here. And then you have halogens. We'll go with the green just because. The halogens are way over here. And then you've got this other thing called noble gases with a nice little bit of purple because of nobility are right there. So you start to see that we can begin to classify lots and lots of these things. Now, these collections of atoms, because atoms are so tiny, we've got to be able to measure them in a nice way. So we use something called a mole. In chemistry, a mole is equal to 6.02 times 10 to the 23rd atoms. That's called Avogadro's number. Avogadro, not Cado. Avogadro's number. So, if we understand this correctly as scientists, what we find is Avogadro's number of atoms is the same. We can say that is equal to the atomic mass. So carbon 12, remember carbon 12 has an atomic mass of 12. So 12 grams of carbon is equal to 6.02 times 10 to the 23rd atoms. It's equal to 1 mole. So now then we can say 12 grams is equal to 1 mole. The abbreviation for a mole is MOL because it's so much shorter. So we start to measure these things together like this. So if I'm looking at carbon and carbon dioxide, what I can see is this thing, whenever you weigh it all together in terms of your atomic mass, would weigh 44 AMUs. But if I want to look at number of moles or number of atoms, number of molecules, then I can convert this thing into 44 grams is equal to 1 mole. Now then I have a way to measure it better. This is a great tool to use for chemists. So these atomic masses make chemists' lives so much easier in so many ways. This mole is a big, big deal. So if I have 36 grams of carbon, and I know I don't want grams of carbon. Remember this? Remember this mathematical tool from way back when? I don't want grams of carbon, okay? What I want to do is get rid of grams of carbon. Right? How do I get rid of these grams of carbon here? Well, I convert it into something else that I can use. How about a mole? So I know from the periodic chart, 12 grams of carbon are equal to 1 mole. So whenever I do this, that means it's 1 mole of carbon. So 36 divided by 12 gives me 3 moles of carbon. So we can start to convert these things into something that are more useful. Now then, instead of having to figure out what 36 is, we got 3. We can use our fingers again. Looky there. So this is kind of where this periodicity, I want to end this periodicity conversation. Because the periodic chart, in the end, this periodic chart that we have right here is the best cheat sheet that you'll ever have. And whenever you start looking at this thing in terms of stuff like the octet rule or energy, now then we have a way to predict lots and lots of chemistry. And that's what makes it the central science.